This video will discuss computing the enthalpy of reaction using the enthalpy of formation of the reactants and the products. Okay, so let's look at a series of reactions here and see what the enthalpy of reaction is for these various reactions. So let's say we have some chemical A, and we want to form A from its elements in their standard state. So the enthalpy for this reaction is going to be the standard formation enthalpy of the species A. Okay, so what if we want to do this for some stoichiometric coefficient A of molecule A, so where A is some integer that's positive. So if we do this, this is just doing this A times, so that's A times delta at F H naught of A. So enthalpy is an extensive function, so an extensive state function, so if we multiply it times some integer, we just have an integer times that specific amount of enthalpy. Okay, if we want to do it for two different elements, we're forming chemical species A and chemical species B, both from their elements and both times some coefficient. Then we have A times the enthalpy of formation of A plus B times the enthalpy of formation of B. Now, what if instead of forming these molecules from their elements, what if we want to take them and return them to their elements? Well, if we do that, the enthalpy, as we said from the Hess's law video, the enthalpy for a reverse reaction is the negative of the enthalpy of the forward reaction. So that's just negative A times the formation enthalpy of A minus B times the formation enthalpy of B. Okay, now similarly we'll do that for another two chemical species, C and D, where they each have their own stoichiometric coefficients. So the enthalpy of this reaction is C times enthalpy of formation of C plus D times enthalpy of formation of D. So if we take these two reactions now and we add them together, what we get is this net total reaction, AA plus BB goes to CC plus DD, where A and B are reactants and C and D are products. So from Hess's law, we know that the enthalpy of this reaction is just the sum of anything that results in this net reaction. So this plus this gives us this. So the enthalpy of this reaction is just the enthalpy of this one plus the enthalpy of that one. So that's all of the enthalpy of formation of our products times their coefficients minus the enthalpy of formation of our reactants times their coefficients. So this says to us that we can find the enthalpy of reaction for any given chemical reaction we choose if we know the enthalpy of formation for all of the species involved in that reaction. So we have a sum over all the products of their stoichiometric coefficients times their enthalpy of formation minus the same sum over all reactants of their stoichiometric coefficients times their enthalpies of formation. Okay, so that all seems nice and well. Seems we have a very convenient way of finding the enthalpy of reaction now, as long as we have species for which we know the enthalpy of formation. So let's try to do an example and see how this works in practice, reminding ourselves of these types of ideas from Gen Chem, which we now have a more strong physical basis for. Okay, let's say the combustion of glucose. We have C6H12O6 solid plus 6 molecules of O2 gas gives us 6 molecules of liquid water. Do I want that to be liquid? Okay, sure. I have it written as liquid. We'll say it's liquid. Plus 6 molecules of CO2 gas. Okay, so all I need to do is look up what are the standard enthalpies of formation of each of these chemical species. Minus 1271 kilojoules per mole for glucose. 0 for oxygen, because it is the standard state for oxygen. O2 gas is the standard state for that element. H2O liquid, minus 285.8 kilojoules per mole. CO2 gas, negative 393.5 kilojoules per mole. All right, so the enthalpy of this reaction is going to be 6 times enthalpy of 6 times enthalpy of water, minus 285.8 kilojoules per mole, plus 6 times the value for CO2, negative 393.5 kilojoules per mole, minus 1 times the value for glucose, negative 1271 kilojoules per mole, minus 6 times the value for oxygen, 0 kilojoules per mole. And that gives us a final value for the standard enthalpy of reaction for the combustion of glucose of negative 2,805 kilojoules per mole.